Excellent. Thanks for the introduction, Ranthony, and thank you all for being here. Thank you to the organizers for the invitation, for putting together this session, which promises to be, you'll have to make your decision about my talk, but otherwise very interesting. And today I want to talk to you about my contribution to this really substantially larger project. You might notice by this list of co-authors, which includes researchers from the undergraduate all the way up to the PI level, but this is, in some sense, it's a data analysis talk. And so a substantial proportion of the work was also data collection, and those people are not explicitly listed here, but I really want to emphasize just kind of, I'm only a small piece of this story. But the story is about electoral redistricting, about the redistricting process, and about a specific part of the redistricting process, which you may or may not have heard of before. And in fact, I hadn't heard of before I was brought onto this project. It's about what are called communities of interest. Every 10 years, a census comes by and each of the individual states start redrawing their electoral districts. And they have a number of criteria that go into the map-making process, one of which, in a vast majority of the states, either explicitly through legislation, through judicial kind of guidelines or policy guidelines, is to try to preserve communities of interest. In fact, as you might imagine, in many of these legal contexts, the definition varies somewhat state to state. This particular definition is the one that we used for a centralized definition. So a community of interest is a group of individuals who share geography and then policy or representational interests. And despite the fact that keeping these types of communities together is part of the guidelines in so many states, in fact, the actual gathering and presentation of testimony, identification of these communities is a quite challenging prospect. As you can imagine, even reading just that definition, it's a nice kind of written definition, but how do you make it precise? How do you point out these communities in a state? And one approach is to try to gather testimony from the public, from an individual member of the public saying, here is a community, maybe several members of the public saying, this is a community. And in past redistricting cycles, this has largely been either by written or oral testimony, if any testimony has been gathered at all by policymaking bodies. So the difficulty with this type of feedback is that, you might have a written piece of testimony saying, this is describing a community, but of course the map makers are looking at maps when they're drawing the lines, right? Just making this public testimony actionable and connecting members of the public with their actual policymakers in this way is challenging, just based on written testimony. So this was the context in which Duchin, her group at Tufts, started looking at the idea of gathering not just written testimony, but also geographic testimony using an online digital web app that a member of the public could go in and say, here is the community on a map, and then describe what the community is. And so they started launching that a couple of years before the redistricting cycle, and then gathering testimony as it came into full steam. And they had a number of these top-line state partners, but again, I want to emphasize that the state partners are essentially the ones who are hosting individual portals for their states. So some government entities, so official line drawers in some cases, who are looking for this nonpartisan kind of data gathering and analysis, but also some community groups in other states. But I wanted to emphasize many volunteers on the ground also helping connect members of the public to actually inputting testimony into this web portal. That's the part of the story before I'm involved at all. And I came in kind of on the technical side of this story, and I'm a computational mathematician, so I started to think about this data, at least in this way. How can we think about the data set that was collected? Each submission consists of a map. And in fact, I can be more specific. So it's a set of census block groups, which you're probably familiar with. These are units of geography that the US Census defines, painted on a map. And then a written testimony, which in this case was a free-form written testimony about, again, what comprises this particular community that a member of the public submitted. And in our most successful states, we had about, say, 1,000 of these submissions. So a substantial number, more than you could really analyze easily just by having all of them on a map, and then, say, like clicking individual polygons to investigate. But at least not, 1 million or 10 million, just to give you some idea of the relative scale of the computational problem there. What did we want to do with this data then? We wanted to create a data analysis pipeline that would start with these submissions and create actionable data products that line drawers, also members of the public, could look at and use to summarize the information, ideally identify at least a proxy for these actual communities that were being testified to by the public, and of course use that in making line drawing decisions. And I want to stress some of the goals here. We really wanted a pipeline that wasn't just an enormous black box. We wanted something, not just actual products, but to have a kind of audible and transparent type of pipeline. It's at least my feeling that as mathematicians on the technical side, we're pretty good at this, right? We have a lot of different ways of quantifying difficult and different types of data, but in ways that we can actually explain fairly readily. And we also, at least this is my approach to this, is that we wanted something that was a kind of additive or direct kind of process, by which I mean we received this public testimony in terms of these submissions and really wanted to make sure that we weren't using a kind of destructive process and creating a data output that didn't allow policymakers to see the individual submissions that they receive from the public, which can be a relatively tempting choice in some manners of data analysis. So we used a two-step process of clustering, and you're probably familiar. Clustering, of course, a very common kind of data analysis technique, breaking the submissions into groups, which in principle, you're hoping to have a procedure to break them into groups which represent each one a community of interest. We did this, in this case, in a two-step process. First, clustering by geography. But you can imagine that, of course, you can have different communities of interest that share the same geography, right? People who are in basically the same place, but they have different interests. And then, so as a subsequent step, a semantic subclustering based on the text. So for the rest of the talk, I'd like to give you a little bit of an idea of a taste of the technical kind of background. And I will mention, if there's one thing to take away, is that in some ways we were making this pipeline in motion, because this was the first census where the data was even available. So the data was being collected. It's, early 2021 or whatever. The census was a little bit late because of the pandemic, of course. So I'm I'm personally, I think we were all very happy with the pipeline that we came up with, but the story is certainly not done. And we'd be thrilled to continue talking to people developing it as we get up to the 2030 census. Okay, some math. So the raw data is in the form of each submission is a set of census block groups and some text. And the first question is, how should one represent this data? Here's the geographic component. And again, each individual submission, so A and B, those could be separate submissions, is a list of block groups. But we could enrich this structure by putting it on, this is an adjacency graph of the census block group. So each vertex in this mathematical graph is a census block group, and you have an edge between them if they share a boundary. So this is a kind of, in particular, what this gives you is a kind of metric structure. The graph distance in this graph is a kind of community distance between these census blocks. Why do I say community distance? It's because the actual individual blocks have roughly the same population. So you can see that, for instance, in, I believe this is Wisconsin, and oh dear, I am forgetting the city that is in the bottom right here, but indeed there's a major city, and that you see densely packed. Is it Milwaukee? Perhaps it's Milwaukee. And you have a densely packed groups because people are densely packed, and they have roughly the same amount of population in each block group. Okay, so this is the first kind of enriching of the structure that we can put here. And somewhat more challenging is taking the raw text and quantifying, making some kind of summary that's amenable to quantification out of that. Of course, your first idea might be to use some natural language processing type method. These are extremely popular for a number of applications. Two reasons why we avoided that. We tested that extensively, in fact, but ended up avoiding it. The first is that we actually didn't have a bunch of data to kind of like tune or train any kind of train model. And the second kind of is contained in the first thing I said, in that many of the trained NLP models are trained on vast corpuses of internet data. There are a number of different concerns about bias in that data. And they're massive black boxes, which makes it difficult to audit. If you make some kind of choice on tuning them, difficult to audit those choices. So and I did not contribute to this labeling process, and I again need to emphasize the volunteers who did. So the decision that the MGGG team made was, okay, a group of volunteers looked at all of the submissions and extracted a list of topics that seemed recurrent across all of them, and then went through manually through each submission and decided on whether or not a particular topic occurred or didn't in each text submission. And so that's the encoding of the semantic content that we used in this case. It's just a list of topics. Of course, one should be interested in the list of topics that were decided, but at least this is an auditable choice, I think was our major advantage with this. Okay, so some flavor of the math involved here. This first part I want to talk about is the geographic clustering. That's the first part of this process. We used what's called an agglomerative clustering process. This is one of the most basic types of clustering one can do. This is a cartoon. And it's a cartoon of a data set consisting of these shapes. I should mention that Anthony is the one who gave me the idea of doing this in a presentation as a cartoon. I like this. And the idea is, computationally, the input is a dissimilarity, maybe a distance matrix between your data points. And if you wanted to summarize all of the dissimilarities, one way you can do so is by iteratively growing clusters out of your data points based off that matrix, based off that data. The output you get is this object called a dendrogram on the right, and you have to decide where to cut the dendrograms is a decision one must make, but when you do, you obtain your groups, your clusters. So like I said, a fairly basic, well understood clustering method. But the question then is, if I'm going to do this based on geography, is what dissimilarity do I want to use between these lists of census block groups? That's the kind of interesting mathematical question. And then you can cut a dendrogram. This one's oriented vertically. And I will mention briefly, again, just hopefully to pique your interest, and if you've heard of such things, the distance that we ended up using is a modified Hausdorff distance. So for instance, if you've ever seen any topological data analysis, or I believe in, that's at least what I'm familiar with, you'll have seen Hausdorff distances. What's the idea here? I'm going to try to describe a dissimilarity between, let's say, this group of census blocks A and group B. And the takeaway is that this distance is, if I wanted to look at the distance from A to B, it's about the kind of the average amount I would have to translate each of the orange nodes to get to the blue stuff. And the average is the modified part of the Hausdorff distance there. So somehow this takes into account size a little bit, right? That's a process which went from A to B, so you have to do B to A, and that's why there's a maximum down at the bottom. But it's effectively the average amount you have to translate in this graph. That's the dissimilarity. You make your cut after describing the dissimilarity and doing all those computations. And this is a heat map of, in Michigan, the Geo Clusters, as we call them, that we got out. So each submission is now in a cluster. It's been assigned based off of this geographic distance. Next step, semantic subclustering. So we've split everything by geography, and now if we want to look at just one of these geographic clusters, it again has a list of submissions in it. We want to split those into some subclusters. This I will be even more high level about. The way that we performed this was based on a kind of, I think you might call this rejection and sampling or a Markov chain type process. So the really high level idea is just start with splitting, say you want two subclusters, right? Split your submissions into two subclusters. And then you can assign a kind of cost based on the geographic and text content associated with the submissions in those two pieces. Right? Like, do these look like two similar by text, two similar by geography clusters? And then, okay, but then you can change it a little bit and look at a new subclustering and say, does this subclustering look better? Quantify all of that, and you can put some probabilities in there and go through this kind of Markov chain process. So I think this will look familiar to those of you who work in the gerrymandering, the computational gerrymandering space. So really high-level overview there. What do the results look like? Here's a first figure that gives you some idea. This is again for Michigan. On the x-axis of this diagram, we have the share of the total state population. The y-axis is the land area. I believe, don't ask me whether that includes water or not. And the size of each dot. So each of these is a cluster after the entire process has been done. So we've done both semantic and geographic. And the size gives you the idea of the number of submissions. So let me say some things. The range, except for the C9 outlier, which, in classical data analysis fashion, we did have an outlying cluster. The range of the population goes from about 0 to 20% of the population. The area goes from about 1/1000th, and those are mostly city-based clusters, all the way up to about 1/10 of the land area. And then from 5 to like 50 submissions is the range on those. give some distributional ideas. And I think, for the sake of time, I will go ahead and move past that. I will end on just briefly showing you one of the web-based kind of visualizations of these clusters that we were able to produce. And again, I want to mention from an audibility standpoint, the button I just clicked, I realized that this text is somewhat small. It said supporting data. And I realized that I don't think I'm connected to the conference internet. But if I were, then you would see a table of the submissions associated with that potential community that we identified in the data. And also, if you were interested in scoring whether a district plan preserved those communities, this is something else that we looked at. Oh, heavens. Okay, and so with that, I will go ahead and wrap up and again say we have our particular process, but we're still looking to improve it. And so if any of that caught your interest, I'm sure any of us would be happy to discuss it with you further. Thanks so much for your attention.
Do we have any questions for our speaker? What was the software that you used for where the map is?
So for this particular visualization, so this is a good question. This web app, it was designed by the team at the MGGG Center. And so this is part of this really impressive effort that I had no part in. Yes, this is Districtor, indeed. So this is the name that they have for the software.
There was a question here first, and then we'll...
So you mentioned scoring.
Yes.
Whether plans actually maintain community submissions?
Yeah, so I will say very briefly, since I went past this slide, roughly speaking, so once you think you've identified communities, right, and they have geography, then effectively you want to make a score where things are good if communities are contained in a district, but communities might be bigger than a district, especially for smaller state legislative districts. So you also want to give credit for, I contained as many districts as I maybe possibly could by population. And so that was the score that we looked at. There's some threshold in here because containment is a little bit annoying, so that's the T.
So you tested this against ensembles of plans or against inactive plans?
This particular figure so there's like a threshold here, but you should understand that, let's see, higher score is better, but you have to look over a range of threshold values. These are just 3 specific plans, and I don't believe any of these were actually, let me not say that. I can't quite remember, but there's no ensemble involved, and that answers that part of the question.
Yes, over here.
Do you have any sense as to how much of an impact the overall work had on the specific state legislatures where you actually built this?
Yes, less than we would have liked. I think I will be completely transparent with you. So much was in motion. My impression, and now I was not the one, Moon's the person to talk to because she was the one going to committee meetings for the ones that contracted with MGGG specifically. So there was some impact, and they were in a few of the reports. But I think that this follows from. This often seems like it has been a kind of secondary consideration at best for any of the line drawers, and I had the impression that it still hasn't quite reached the level of impact that we would have liked.
Yeah, and maybe follow up for future, so you actually have some data. I don't know what the level of proprietary nature of this is, but could you
Yes, absolutely.
That would seem to be the way that the field could move toward 10 years from now, at the next redistricting, develop more clear methods that could be better communicated to legislators.
Indeed, and so the data is public, and it's contained at this GitHub link. I agree with you, and I think something about I think somehow the visualization. My impression was like we kind of didn't have it tied into the software that they were using like soon enough to really like get in on that, but indeed.
Great, thanks. Thanks, AJ. Thanks, Anthony, for the invitation. Yeah, so I'll talk about a couple different projects. One is with Moon Duchin and Thomas Swayhill, and one is just with Thomas. Both are about kind of applying tools from geometry and topology to study this redistricting problem, which you've already seen a bit about. Okay, so yeah, let me talk a bit about redistricting. So this has been mentioned in the first couple talks already, but remember the point is I have a state, it gets cut up into districts, so I partition the state into some fixed number of districts. Occasionally this is redone from time to time in a process called redistricting. The districts are required to satisfy certain rules, so roughly equal population within a given tolerance. Okay, that's pretty clear. Contiguity just means topologically connected. Okay, and those are kind of the well-defined rules. There's also something that people call compactness. This does not mean topologically compact. This is kind of saying you don't want the boundaries to be too wild in some sense, but that's very vague. You want communities to be preserved, like Parker was talking about, and racial fairness and other things like this. But the first two are pretty clear. The rest are a little bit more up to interpretation, but that's the idea. Okay, so gerrymandering is the practice of drawing political districts for political advantage. So kind of bad faith map drawing to kind of bake a certain party's advantage into the structure of the state voting. And so that there are well-known ways to do this. So, in this little cartoon picture, even if 60% of a state is blue, depending on how I cut up the districts, I can make blue win all the districts, or I can make red win a majority of the districts, doing this kind of packing and cracking type move. So if I fill up some of the districts like extremely heavy majority blue, then I can squeeze out extra districts for red, basically. Right, okay, so kind of the very high level thing that we want to do is to quantify gerrymandering somehow. And there are classic ways to get at this. So kind of early attempts were to go after this kind of compactness idea. So how wild are the boundaries? If you see kind of old school gerrymandered maps, the districts look pretty wild. And you can tell that there's something, people were up to no good in the way these are carved out. This compactness score, the Polsby-Popper score, is really just kind of measuring how far you are from isoparametric inequality type thing. So the disk is kind of like the highest score you can get here. And then as your boundary becomes more complicated, the score drops. But so the old school gerrymandered maps, you look at them and you can tell that they're gerrymandered, but as people got better at this, you can gerrymander a map perfectly well with reasonable looking districts kind of visually. So this isn't super useful these days. It makes sense to incorporate kind of voting records into your measure of whether a plan is gerrymandered. So there's something, for example, called the efficiency gap, which in some sense is measuring the wasted votes between parties in a given election for a given districting plan. The kind of what I would call the modern approach, which came up in Anthony's talk, is this kind of generating ensemble of plans idea, right? So somehow we generate an ensemble of random plans for a state and then look at voting records and kind of analyze the statistics across that ensemble and say, okay, so I get some distribution of outcomes across the ensemble. I look at where does the enacted plan lie in terms of outcomes, and if it's an extreme outlier from the distribution, then that gives you evidence that perhaps there was a gerrymander. Okay, so a lot of this talk is based on this idea of generating random plans, so let me say a word about this. So districting a state you can think of as a graph partitioning problem. So the state is kind of very finely divided up into precincts. I can turn the collection of precincts into a graph by taking the kind of dual graph. So I get a node for each precinct, and I draw an edge if they're connected. And then the task is just to partition this graph, partition the nodes of the graph in a way where partition blocks are connected, population is roughly equal, and then you can try to satisfy these other kind of less firm rules as well. So one way to do this, due to the MGGG group that we've already seen come up in the session so far, is called the Recom algorithm. And this is this very simple idea. So you think of it kind of this as like a Markov chain. So given a districting plan, now I'm going to update that districting plan. What am I going to do? I'm going to pick adjacent districts, take a random spanning tree of those nodes, pick an edge at random, and cut it. So then this gives me a new partition between those two adjacent districts, okay? And so this needs to satisfy rules, so you make a proposal like, am I allowed to make this cut and still have the population property preserved, for example? If not, then you make another choice. But in the end, you run this thing, so start with a plan, update, update, update. You run this, say, 10,000 times. Here's showing every 2,500 steps, and you get these really pretty diverse-looking plans for the state. So at least empirically, this seems to be like mixing well and giving you reasonable plans in your ensemble. Okay, so as I already said earlier, the kind of modern approach to studying this gerrymandering problem is to generate an ensemble plan, say with this Markov chain process, look at voting records and create a distribution of outcomes over your ensemble, and then kind of study enacted plans. Where do they sit in that distribution? So the work that I've been involved in is trying to kind of see how the geometry of the districting plans comes into play a little bit more. And so I'll describe these two projects. The first is using tools from the field of topological data analysis. The second is using tools from the field of optimal transport. So I'll say a bit about what those mean as we go. So I'll mention like really, well, especially Moon, but also Thomas are really the experts in gerrymandering here. So from here on, this is more of like a math talk and my contribution to this. But if you have any technical questions about politics, maybe I won't be able to answer them. Okay, so let's start with the first project. So this is TDA and gerrymandering with Moon Duchin and Thomas Wayhill. So here's the idea. So this is using something called topological data analysis. Roughly, this is this field where you study data by looking at topological features of your data set at multiple scales. But that's the high-level picture. You don't really need to know what it is in general, because the application here, I think, is pretty natural, in my opinion. So here's the idea. So starting with a plan, the outcome is I want some kind of summary statistic of the geometry. Okay, that's my goal. What am I going to do? So I start with my plan. I construct this dual graph. So there's a node for each district and then edge if they're connected. Now I take the outcome of some election and I put, say, the share of Republican votes on each node. So I have a function on the nodes. So I attach a number between 0 and 1 to each node. And now here's the multi-scale aspect. So I'm going to, in TDA, they call this filtering the graph, whatever. So I'm going to create kind of a sequence of subgraphs, okay? So I'm thinking of the vote share of Republicans in this election, starting from 0 at top to 100% at the bottom. As I cross thresholds where, I guess the lowest district had like an 8% Republican vote share. So once I pass that threshold, I throw in that node into my subgraph, okay? Once I pass 37%, then I get a few more nodes thrown in. Whenever I'm able to throw in an edge, I do, is the rule. Okay? And then going along up to 100%, I get this sequence of subgraphs. At 100%, I get the full graph again. Okay? All right, so then now I'm going to use the kind of simplest topological feature that I can think of, which is connectedness, and say how many connected pieces are there of these subgraphs as I move along. Okay? So here I have one connected piece, here I have two connected pieces, here three, but then in the next step, two of them kind of merge together, so I don't get a new one. So I'm thinking of the topological features as being kind of born, a new one born, a new one born, and then this guy kind of dies when it gets merged in the next step. So then I just record those births and deaths of features in this thing that they call a persistence diagram. But that's all this is. It's just recording when is a topological feature born, when does it die, and the rule for dying is that the thing which is born later, dies when it gets joined with something born earlier. Okay? Okay, so you end up, the pipeline is districting plan, summary of the kind of connectivity subject to the plan's kind of graph structure and the voting information on top of the nodes. So it's summarizing all of that at once is the idea. Okay, so then we have some kind of mathy stuff in the paper. So the space of persistence diagrams, so think about the space of all diagrams of this type, has a kind of canonical metric that people use called bottleneck distance. Roughly, it's about, I want to measure the distance between two diagrams. I find kind of an optimal way to match points. And then I associate some cost to a matching, and that's where the optimality comes in. That's as much as we need to know, I think, for this. So we have a theorem which says that, okay, this would be a bad thing to do if I could take a districting plan, make a small move in the Markov chain, and it completely destroys the structure of the persistence diagram. This would be bad, because then this would be completely unstable to the kind of data that we're using. And the theorem is essentially saying that that doesn't happen, okay, in some technical way. So, and this is really coming from kind of classical results in TDA, but the point here is that it's quantified in terms of stuff that's relevant for districting. The kind of algorithmic thing that we were using here is that we compute something called a Forshaming. So if you haven't heard of this before, this is this nice idea which says if I'm in a metric space and I take a bunch of points in that metric space, well, if that metric space were Rn, I would know how to take a mean of those points, right? I add together the vectors and divide by the number of them. I can formulate that as kind of this variational problem, and then that formulation works in an arbitrary metric space. Okay, so optimizers of some objective function are called Forshamings in a metric space, but this just means like take a mean of a bunch of points in a metric space in some sense. So there's an algorithm to do this for specifically the metric space of persistence diagrams and bottleneck distance due to Turner, Maleko, Mukherjee, and Harrer. And the output is, if you're trying to understand what this means, so I have, say, look at this. This is some ensemble of districting plans where there's 203 districts. So this is just kind of overlaying all the persistence diagrams on top of each other. So this is, 1,000 different persistence diagrams or something. The Forshaming is the red points here. So that's kind of the mean diagram according to this algorithm. Great, so then Forshamings were quite useful, and basically the type of analysis we do using these signatures, it's pretty varied. We can look at, so given an ensemble of plans, right, compute the persistence diagrams for that ensemble, compute the Forshaming of that set of persistence diagrams, and then use that to do analysis on the ensemble. And the types of things that we're able to see from this perspective are kind of locating important regions where you have like high blue vote share surrounded by low red-blue vote share, for example, across the ensemble, given an election. In this experiment, we generated two different ensembles, one which was biased to try to gerrymander for red, one which was biased to try to gerrymander for blue. And you get different ensembles of persistence diagrams, or different ensembles of districting plans, which you turn into diagrams. And you can see kind of which regions in the state, this is North Carolina, which regions kind of matter from a gerrymandering perspective. Okay, so regions like Asheville, it doesn't really, when you're trying to gerrymander, you don't really care so much about how you're splitting up the Asheville region, basically. And you can see that in that the red and the blue persistence diagrams don't really look statistically different from each other. Whereas the Greensboro region, there's a big difference between red and blue, and this suggests that this is a region that kind of matters precisely how you cut it up when you're doing your gerrymandering. We can also look at the Forshaming of the ensemble compared to the persistence diagram of an enacted plan, and look basically for outliers in the structure of the plan. Okay, and then let me quickly also discuss this other project, which is using something called optimal transport. So this is trying to address a related problem, which is like, okay, so we like to have, take ensembles of plans, look at kind of plan-wide statistics, and then look at the statistics over the ensemble, right? It'd be nice if we could look at kind of district-level statistics. Okay, this seems like very desirable, but the issue is that that's really not well posed if I'm looking at two different plans. So here are two different plans. How do I say like that there's a common thing I'm going to call District 1 between these two? Okay, for some regions it's more clear, maybe like pink here and light blue here should be called the same district, but it's less clear maybe how to match up like this light blue and dark blue across these three regions, for example. So there's no kind of ground truth what I'm going to label the different districts in my plan. So that's the problem, is how do I come up with a labeling across the full ensemble which is consistent and well-reasoned. So then, of course, we turn this into a math problem, and we say, so this is a math problem now, so we should generalize it to some degree. So we think about these things called symmetric products and say, given a set, the nth symmetric product of the set is take the usual product of the set n times, but then mod out by the action of the symmetric group, which permutes entries. Okay? So you should think of this, the things that live here are like unordered n tuples of points in the set X. Okay, so I'm forgetting the ordering in the kind of the coordinates. Okay, so why is this relevant to districting plans? See, the idea here is we're going to take, say, Y is the map of the state, so the overall kind of outer boundary. I'm going to think of a districting plan as a collection of probability densities over the state. And there are other ways you might do this. You might say, okay, maybe a district should be like just an indicator function or something. The reason we use probability measures is because the space of probability measures is a thing that we were comfortable using as a metric space, because this has a essentially canonical metric called Wasserstein distance, and computationally this is very familiar to us. So here we're going to think of each district in my plan as a probability density. So then the plan itself is a collection of probability densities, but I don't have some canonical order of them. So I should think of it as an unordered collection of probability densities over the state. Meaning that I'm going to model a plan as a point in the symmetric product n times, or n is the number of districts, of the space of probability measures. Okay, so then we define a metric on the symmetric product, assuming that your set was a metric space to begin with. This induces a metric on the symmetric product, which is, okay, in symbols it's this, but it's like more or less the thing that anybody would come up with, I think, which is to say, given an unordered tuple, or given a pair of unordered n tuples of points here, what's the distance between them? Well, I'm going to take like an LP distance on the product space, but then I'm allowed to shuffle the order of one of the tuples. Okay. So this is exactly like the kind of quotient metric. So we prove some theoretical results about this in general. So this is like not so relevant to gerrymandering, but we're mathematicians, so we prove things about how the curvature of the kind of induced metric space, the symmetric product space, relates to the curvature of the original metric space, things like this. This is curvature in the Alexandrov sense. But yeah. Okay, so this is a nice theoretical result, not so useful for gerrymandering. On the practical side, for things like gerrymandering, we develop a Forshaming algorithm in this kind of weird metric space. Okay, so given now an ensemble of unordered n tuples in my metric space, I can compute a Forshaming in that metric space, which is useful because that's exactly the kind of data we have. So I have a districting plan for North Carolina I'm thinking of as a point in the 13 symmetric product of probability densities over the state, okay? And then I have an ensemble of 1,000 plans. So I have 1,000 points in this weird metric space, okay? A little technical point is that the probability distributions, then we're modeling those as empirical distributions, so a bunch of points. Okay, so given our ensemble of 1,000 plans, we can compute the Forshaming, which should be like the average districting plan. And this gives us a ground truth label for every district or in a particular plan by matching that particular plan to the Forshaming. So now any plan in my ensemble, I can label every district with a number, 1 through 13, and this can be done consistently across the data set. Then the point is now I have district level statistics. Okay, so now I have a ground truth district 1, and I know what the voting statistics look like in that ground truth district 1 across the voting, across the ensemble. And I think that this is quite a useful tool. So just for an example of how you might see how this works, we have, so in the background, these are the statistics across the ensemble, the box plots. Now, given an actual plan, so this 2012 plan, I match the districts of this thing to the Berry Center, so I can label the districts in this actual plan. I can look at the voting outcomes, and I can see that this looks like kind of wildly out of distribution at a district level, okay? Which is not so surprising. I mean, this is one, I was saying old school gerrymanders are obvious. Like looking at this disgusting map, you can see that this is gerrymandered just visually, right? Look at these things. And you can see that like this yellow, extremely wild district, the voting outcome in that district was extremely out of distribution for the ensemble. So it's still pretty gerrymandered, even though this looks much tamer. So I said that you can do this, so you can kind of get around this compactness thing and still gerrymander. This is a plan that was created by judges purposefully to not be gerrymandered, and you see that the outcomes are much closer to being in distribution. And here's the 2020 plan, which seems much milder. Okay, so here are some references for these papers. Thanks to NSF for supporting some of this research, and thanks everybody for listening.
Do you have any questions for our speaker? Parker?
So, how does this compare to the standard like ordering based alignment?
Okay, that's a good question. I had a slide that I deleted, and I can't remember. I think that they were not too far off, but there was a detectable difference, but that's an extremely hand-wavy answer. But I can pull up the slide later. We can look at it. Yeah.
There's a question in the back.
I just wanted to get clarification on one thing you said. I think it was when you were showing the topological data analysis pipeline, and you said, did you say the rule for dying is the thing that is born later?
Yeah, let me say it again. So the rule is, so let's look at an example. So this red component here was born later than this blue component. So when these things merge, the thing that dies is the thing that was born later.
Oh.
Last in, first out.
Yeah, exactly.
Great. Okay, thank you.
Yep. And this is like the standard rule that people use in TDA. Yeah.
Like when companies downsize.
Precisely, yeah, seniority. Yeah, so we did North Carolina, and I think we did Pennsylvania also in the TDA project, and I think we mostly just focused on North Carolina in the optimal transport project. But the code is all there, so provided you have the geographic data and the vote data, like the pipelines just go through. But it's a matter of being able to use also like the gerrymandering software and generating these markup chains, things like this. But in principle, this is just generally applicable. Yeah.
Particularly interested in how you locate this region, like for gerrymandering.
Right, yeah. I think that's kind of one of the more interesting things that came out of that.
Does this framework change dramatically if there are, say, 3 parties or 4 parties, say England where there are lots of different political parties?
Oh, that's interesting. I mean, we've only run this on kind of US-based stuff, but yeah. I mean, and especially, we're using this filtration, like implicitly you're assuming that everybody votes one way or the other, so that filtering Republicans captures the whole thing. I guess you'd probably need to use multi-parameter persistence, right, where you have multiple functions you care about. And then the answer is yes, this changes dramatically, and it becomes much less even tractable computationally to handle this. But I think would also be interesting. Yeah.
So I do want to make a statement about the importance of having inclusivity in various spaces. Disrupt MathFest is a thing that is a branch from Disrupt JMM, and it's just raising awareness of all the different discrepancies that different people are facing, especially with us being in Florida. I just want to represent myself as an ally in this space and make sure that people understand that being a mathematician is more than just being a scientist, but also being a human. And without further ado, I will start my presentation. So I know that there was a beautiful land acknowledgement that was given earlier, but I just want to further highlight the painful history of stolen labor, genocide, and forced removal from this specific territory, and pay my respects to the Tocobaga, Miccosukee, and Muskoka tribes. As a call to action, I also ask that you donate to the Trail of Florida's Indian Heritage, which there are different websites all over the country for different tribes, things of that nature. So here, there is a QR code in case you're interested to donate, and I will go into my outline. So first, what is TDA? I'll go over an introduction, give a little bit of background, and explain what persistent homology is, the Wasserstein distance, and our main method. If this presentation seems very familiar to the one before, so far it is. There is a lineage between Moon Dushin, Tom, Needham, and then Thomas Whale, and then myself. Thomas Whale is actually my advisor who helped me with this presentation and did this work with me for my master's thesis. So there's a lot of persistence homology and things of that nature that might seem familiar. After that, I will go into my methods, go into the many applications that we looked through for this work, and then my final conclusions. So what is TDA? Topological data analysis, again, is a collection of methods for discovering the shape of data. This includes methods such as clustering, manifold estimation, nonlinear dimension reduction, mode estimation, all the things. But specifically, I'm going to focus on persistent homology and kind of try to re-explain some of the things that Tom was saying before as to how we look at persistence diagrams. So in our work, we'll use persistent homology to detect and visualize the presence and magnitude of peaks in a population share respective to particular minority groups, in this case, Black or Hispanic. These peaks correspond to high local concentration of particular populations. The number of peaks and the values near in between tells us a lot about how a particular population is distributed, and the output of the persistent homology method on a particular region is a persistence diagram, which summarizes all the information, as Tom said before. So this is my diagram to try to explain the birth and death conversation that was held earlier. So in our case, we're looking at 0th dimension for persistent homology is there a laser? There's a laser. So in the first square, you see we have just one connected component. It's just one piece. In the second square, there are 2 because this circle is not connected to this line segment. So then in the third and fourth, we also have one connected component. Everything is connected to each other, so that counts as 1. Now, I do want to pay attention to the fact that we can create a persistence diagram based on when something is born and when something dies. So again, we see in the second square, this circle is born at 2, and it connects here, which means it dies. As we said earlier, last in, first out. So that's why we plot it here, born at 2 and dies at 3. And then the first in, which was this one, born at 1, technically doesn't die, but we just say it dies at 4 because that's the last square that we have. This is our definition of a Wasserstein distance. We used a 1 Wasserstein distance. I know Tom mentioned the p Wasserstein distance. You can change that value to any number that you want. We used 1. We hope to use 2 in future implications. But essentially, in short, it's just a measure of distance between 2 different persistence diagrams. Our methods. Time. Oh, great. Okay, so first, we imported 100 city shapefiles, and we used the largest US cities all over the country. So we imported those 100 city shapefiles and generated dual graphs for each one. We construct persistence diagrams and generate super level set filtration using either Hispanic or Black percentage, which is what Tom was mentioning before when you filter out by different percentages. And then we computed the actual Wasserstein distances between each pair of cities and between 2010 and 2020 for each city. Again, I said that we're using census data, so we want to make sure that we're just paying attention to 2010, 2020 for now, but hopefully in the future, we'll be able to use 2030 as well. So a city shapefile is a geometric structure that defines a large amount of data. Specifically, we're using North Carolina for this image because, of course, I did this work with Dr. Thomas Whale, who was at University of North Carolina in Greensboro. So this is an example of what a census tract looks like. I keep not using this. So this is Greensboro. This is kind of what it looks like before as a city shapefile. And then here, these are the nodes that Tom was mentioning before. And then these are the edges that you can connect to each one just to represent every single tract. In one of the presentations earlier today, there was a mention of census data blocks. We're using tracts, which are a little bit smaller. So we have a little bit more of a finer, more precise understanding of what's going on in these cities. So if none of that made sense, I have a main method slide. So essentially, we take any city. In this case, we have Chicago. We take any city, and usually when you see something like this, you see it in a gradient scale. So from 0 to 100, ranging from white to dark blue, you can see that this Hispanic population increases. There's not a lot of people of this particular demographic in these areas, but there's a cluster here which represents some high percentage of a Hispanic community in that area. Usually that's what we see in the news or anywhere on social media. In our work, we're going to filter it out. So this 90% represents communities that have at least a 90% population, and then so forth down to 0 until we have a complete filtered system. From that, we then go back to what we discussed before with our connected components, what's born and what dies, and we plot it here on our persistence diagram accordingly to the percentages given in our filtration. We do that for all 100 cities. It's a lot of talking. Okay, so these are our applications. First, we're going to go into single city results of what we get from the persistence diagram looking at Chicago alone. So first in 2010, I'm not using the mic. In 2010, this is our persistence diagram for Chicago, and we notice these 4 points here. I do apologize. We tried to use a particular gradient scale for anybody who may be colorblind, so I hope that you can see it, but if not, I will point it out. So this circle here, this one close to the infinity sign, this one, and this one, were points that we consider to have the most interesting demographics about these communities because they're furthest away from the diagonal and closest to that infinity sign. So that indicates that something is going on there where there is high population, but it's giving a level of segregation. So that's in 2010, and then we notice in 2020, I don't know if you could see it, I'm gonna go back, look at the red dot. So the red dot's on the left in 2010, in 2020 it moves to the right. So this shift is something that we noticed in our work and we're interested in what happened. So of course, Dr. Whale, being the historian that he is, looked into it and saw that this shift occurred because 1,000 Black people moved from one housing project to another. And so that shift is something that you can uncover when you do persistence homology, but it's not something that you can uncover just looking at different tracks or district lines being drawn in different ways. But this shift allows us to kind of see that something is happening in this particular area and then allows us to dig deeper and see what's going on. Next, we'll talk about trends and outliers. So to do that, I need to talk about a city-to-city comparison. The easiest way to explain this slide is imagine that I have 3 different cities, and I'm looking at the persistence diagram, and I'm computing the Roche assigned distance. If one city is 0.2 away, if city A is 0.2 away from city B and 0.3 away from city C, then B and C have to be within some other range to complete the triangle, so I can explain exactly how far each city is from each other. When I have 100 cities in this case, it's a lot harder to compute that for all 100 cities against the other 100 cities. So we use multidimensional scaling here to give us this visualization that we can't typically comprehend on our own. And then we use the local outlier factor method for these Wasserstein distances. It's an algorithm proposed by Brunig et al. In 2000 that allows us to find anomalous data points by measuring the local deviation of a given data point with respect to its neighbors. It just tells us what the outliers are once we compute everything within our MDS plot. And here we are. So in 2020, for the Black community, we have this cluster here and all of these outliers. Similar to the Hispanic community, there's only one cluster in all these outliers. When we ran this originally, we were assuming that we would find multiple clusters. So doing the MDS plots and finding that there's only one cluster for each racial demographic was very interesting. And then also we were able to identify the outliers. And further, most of the outliers are all of the larger cities. So New York, LA, Chicago, these are some of the biggest cities in the country, but somehow Boston kind of snuck its way in there. So that's something that we can uncover by, of course, still using persistent homology and understanding what this looks like and finding these different trends, these different outliers. There's all these different applications that we can do with this work. I'm very excited. How much time do I have? Okay, so then we looked at the comparison between Black and Hispanic population across total population and total persistence. So total persistence, essentially, it's on my slide, is the sum of death and birth, is the sum of the difference from death to birth for each point. So you take that difference, the Wasserstein distance from death and birth for each point, you sum them all up, that is your total persistence. We did that for all 100 cities and correlated it to the total population and found that for both racial demographics, there is a 0.9 correlation, that R coefficient, that shows that there's a very strong linear correlation between the two for 2020 data. And then we saw for San Antonio for the Hispanic community and Detroit for the Black community, these are large cities that did not have persistence diagrams that looked like the other large cities in our work. So that became interesting to consider what's going on in San Antonio and Detroit to not have as many persistence points on our diagram as other large cities. And then looking at the Chicago-Houston comparison for the Black community in 2020, we see that this persistence diagram has a huge empty gap here, whereas Houston has filled in persistence points here. But the interesting thing about these cities is that both of them have a very similar population, a very similar Black population. So if you have, I'm gonna make up a number, there's 20,000 Black people in Chicago, 20,000 in Houston, you would expect the persistence diagram to look similar because they have a similar proportion of Black people, but that's not the case. So, again, just uncovering a lot more information about things that you typically can't see when you're just looking at data given to you from the census or the news. So then, Phoenix was another interesting city that we saw because Phoenix has a very low Black population. It's about 7%. I think the highest track percentage in Phoenix was 33% for just the track, but across Phoenix it's just 7%. And this did not have nearly as many points in its diagram, nor did it have as many outliers, so it's very, very low, and we just wanted to point out that this can also be something that happens when you look at a city by itself. And further, even if you look at the graph here, remember I said before, this gradient allows us to see different percentages of a particular population, and this stronger blue doesn't even exist in our choropleth, is what this is called. This is a choropleth. I learned that. So sometimes it's easy to say like, oh, like it's not a very, very high population, but other times it's easy to see like of course, what we said before, sometimes we can dictate where those neighborhoods are based off the census tracts. We can go back and say, oh, this census tract has to do with this particular neighborhood, and that neighborhood is low or high population or whatever based off our persistence diagram. So looking at change over time, this is all 100 cities. I do apologize, it is very small, but this is all 100 cities looking at both Black and Hispanic populations. So starting at New York, which is our biggest city in the country, and going this way, sorry, that's just how it was plotted. I'm sorry, it's right to left, but I guess that is inclusive for other communities, right? We don't all read left to right. So starting at the right, New York, and then going this way, and then further at the top, going right to left again, to our smallest city, which is Spokane, Washington. Anybody from Spokane, Washington? No? Okay. It's our smallest city in our diagram. So looking at this, we can see for the Wasserstein distances for each city from 2010 to 2020, what that relationship looks like. So for the Black community here in blue for New York, there's a significant difference, but it's pretty much the same for the Hispanic community. They're relatively similar in that regard, and that's the case for a lot of our cities, except this is a closer up image of what that looks like that I was pointing to before. This is New York. Oh, this is New York. And so, except in cities like Pittsburgh. So Pittsburgh, Pennsylvania, there's a significant shift of the Black community and then not as so significant for Hispanic community over the course of 2010 to 2020. And of course, you can look at any of the 50 cities and find these comparisons, but we looked at Pittsburgh in particular and looked at their persistence diagrams. Now, what we did notice for the Black community that had that shift, from 2010 to 2020, the persistence diagrams are a little bit different, but they have a very similar structure in the sense that their persistence points are scattered throughout the entire diagram, implying that there isn't as much segregation, but there are a lot of mixed communities. So instead of there only being one or two way over here points for either timeline, indicating that those communities have a high population or high proportion of a particular racial demographic in that area, there's a mixture in the middle as well. So for both 2010 and 2020, these demographics were mixed throughout. So even though there was a significant shift, they still were similar across time. I've got 4 minutes. So I'll talk about the clustering analysis. Our k-means clustering algorithm is, like Tom was saying before, we use our Forshaming. It's going to average all the information that we have for our persistence diagrams, and it just gives us an opportunity to look at things in a more concise way. So I'm going to skip through some of the slides a little bit. We chose k equals 5 for our elbow plot just so that we can distinguish across 5 different categories for our information. And these are our persistence diagrams within those particular clusters. So for the first cluster, this is only 2 cities, but both of those cities have a persistence diagram that look like the blue one. For the second cluster, every city that's in this cluster has a persistence diagram that looks similar, and so forth. So we did it for all 100 cities, and you'll notice that for the last 3 clusters, there's a point here, and there's a point way up here, and there's a point way over here. So for the third cluster, this indicates that there's a highly segregated community for some population over here. The fourth and the fifth have low percentages. And you can figure all this out in different ways based off how many clusters you have, but these are the 5 that we chose. So as I said before, these are the 5 clusters, but for the Black community, we notice that the first 3 clusters have a similar proportion of Black people in their area, and the last 2 are very small. For the Hispanic community, these are their clusters. The first one looks kind of similar to the first cluster for the Black community, just because there's so many persistence points, and then there's even fewer here. But again, still seeing that segregation here at the top left for the third cluster, fourth and fifth, something similar. And then here are the statistics as well. Again, we have very interesting demographics, but almost 50% of the communities in the third cluster are Hispanic, and then very, very low on the fourth and fifth. So some similar relations between Black and Hispanic populations. And then one of the biggest drawbacks is the modifiable aerial unit problem. This is an issue because when you try to draw the district lines, sometimes there's a bridge, there's a new highway, there's a river, there's something. So when you're drawing these district lines, it kind of gets in the way of things, and that really affects our work from time to time. But you can see in our blue circle, there's a shift from left to right, literally because this track was split into two different percentages based off of how the district lines were drawn. I'm running out of time. So then, this is an example, San Diego, we have here, where a lot of the persistence points are closer to the diagonal, and then on this side, we've got 1 point way up here that didn't exist before. So from 2010 to 2020, again, based off how they're drawing those lines for the census tracts, we will have these issues. Okay, in conclusion, 1 minute. So we want to add to the growing literature on applications of persistent homology, but I do want to point out we are not the first to do this work. Social scientists have been looking at this work for decades, if not centuries. We're the first to use persistent homology and look at it in this way, but people have been studying racial demographics forever. We demonstrated how persistent homology provides a range of quantitative surveys over the 100 cities and their demographics. I talked about the MAUP issue, dealing with separation by water and drawing those tracks. More robust clustering techniques is something that we want to do in the future. Investigating other persistence statistics beyond just the total persistence and looking at how that correlates to population of cities. Our work also underlines the need for following up persistent homology analysis with a closer look at the underlying data, guided by the location information connected to the persistence diagram. And then on their own, we can obscure important information, and it might be misleading, again, with the MAUP error, things of that nature. In the future, we hope to connect quantitative analysis provided by persistent homology to concepts from the social sciences and detect demographic shifts with this information is just the first step. So we hope to lead a search for social forces behind these shifts, and then rely on the established ideas and kind of have mixed methods and studies of mathematics that's incorporating social justice from that perspective, and it's not just, oh, we're mathematicians, we know it all. No, we don't. And so this is our preprint and the code. If anybody is interested in following up with our work, this is a QR code so that you can look at what we've done. Let me know if we did it wrong. Totally kidding. And then I would like to give my acknowledgments to the NSF who's funded me. I am a Bridge to Doctorate Fellow at Clemson University. I did this work at University of North Carolina in Greensboro under the supervision of Dr. Thomas Whale. And I would also like to thank my ISERM village for allowing me to be the human that I am within this mathematical field. And once more, before I finish, if you came in a little late, please donate to the local Native and Indigenous tribes here in Florida. That is the QR code in the bottom left corner. And once again, I am very much an ally and supportive of the queer community, and I appreciate you all's time. Thank you. I'll take questions.
Thanks. Yeah, I'm at Bates College, though I've been on sabbatical. Some of the work you've heard in the session, you might have heard ISERM and MC. Those are two math institutes that I've been spending my sabbatical at. One in Providence, that's Providence right there, and one in Chicago. That's actually the picture that you're seeing there. So I'm going to talk a little bit about some projects that we've been working on, community-driven, data science-oriented. A little bit about myself. There's a lot of things. I'm going to point out a few things that are relevant here. For the first project is that I'm from Rhode Island. So for me, when I was thinking about how I wanted to do some data justice work that was really going to push me as a scholar, I wanted to go back into the communities I came from and go contribute back. And what do I mean by the communities that I came from? Well, in particular, the origins of a lot of my social justice work happened within the Spanish-speaking Catholic churches that my dad was a part of, where we helped a lot of immigrant families because my father was an immigrant from Peru. And so I think that is something that was stayed with me for a long time and informs kind of my perspective on that work. And then I hold a bunch of other identities in a bunch of other places, and hopefully you'll see those come up as we go forward. So originally I was just going to talk about the MC work, what I put in this, but I'm going to actually also anti-justice legislation. I should have put it slightly different, but I threw in a few slides from another project that's very, very recent. So this is like hot and breaking, and so you'll get. I'll run through some of the other stuff so that I can try to get to some really cool new work as well. So I mentioned that I'm from Providence, and I really wanted to find community partners in Providence. And the way that some communities, and my community works, is they have a phrase called "you know a guy who knows a guy." It's just a phrase, but the idea is there's like a really small world network that exists, and this is how you find relationships to broker partnerships. And my sister still lives in Rhode Island, and she works a lot with the Woonasquatucket River watershed. Woonasquatucket is an indigenous word. It means where the salt water ends, and so it is it opens into the Narragansett Bay of the Narragansett people. And if you'll kind of notice, Brown University is to the right of Providence, and kind of it's sort of a whole college town, but to the left of the river is also Providence. You'll see there's a consulate of Guatemala. And we were working with a particular organization that maintains this river that it's just above that Route 6, and focuses primarily on helping neighborhood advocates learn about how to advocate for natural resources in the community of Olneyville, which is highly subjected to flooding, and the river at one point was one of the most dioxin contaminated rivers in the US, and so there's also river contamination. In addition, compounding the flooding issue, the old sewer system of Providence is a combined sewer system, which means that when you have extensive rainfall and it overflows, it is pulling sewage up. So it is not just water that is contaminating. So this is the program that started in 2020, so everything was kind of on Zoom. But they really wanted to help people connect together, and then also connect about advocating for their neighborhoods, for their people, right? Because this is a very place-based sort of advocacy work. And two of the folks who were involved in this early 2020 cohort were Maria Jose Gutierrez Paz and Jenny Mercado. And both of them went on to become facilitators of the next cohort and the next, and so forth. And so, and they've had great track record overall of getting placed also into city council positions and other kinds of positions of influence. So this is not just like a program to help you feel good that you're helping this neighborhood. They're working, they're putting people in the right places. So I want to talk a little bit about what it meant for us as a community that was kind of coming into this research center with Brown. And honestly, WRWC has not had the best experiences working with the ivory tower. They write them into a grant to look good, and then they may or may not follow through on all the promises, and for very little money than it's worth. So I think this is something about relationship repair that we need to think about, and how we approach partners. Is this a one-time thing? Is this a full investment? And these can work a lot of different ways. But I just want to point out a few features of what makes this work so humanizing and so important, and so directed by the community that we're working with. One of the first things we did after having this hey, meeting, hey, is this something you might be interested in working with mathematicians? And after they were not scared off, then we went and hung out with the whole group. And what that meant was going to their headquarters, bringing food to them, hanging out. The whole meeting was in Spanish. In fact, almost all the working time with Nuevas Voces has been in Spanish primarily. It meant taking a walk along the Woonasquatucket River to understand what that community was like and what it could be, and really understanding the place that was so important. And finding compensation too for the work that we were asking of them. Our conversations really started because of environmental information. The nonprofit that hosts Nuevas Voces and Championes, they are at a watershed restoration focus. They're really nature advocacy, green justice. So we started talking a lot about what kind of information from that perspective do you need, but it became abundantly clear that as we were talking, they wanted a broader perspective of community advocacy information. So they're very excited about getting their hands on data, using having data accessible in a way that they needed it. But the data that we ended up talking about the most was not the flood zone data. It ended up being data about where can I get help? How can I find health care? What school should I choose? And this is really important, because how do you advocate for your community if you're worried about what your kid's going to eat every day, right? You got to treat it like as a whole holistic problem. So we kind of blew up, we kind of expanded what we were going to do very quickly. Now the other thing too is that I'm going to point out some features. There are many platforms that already exist for data aggregation of some sense or have data for some sense. And one of the biggest challenges is that it's not relevant for community advocacy needs. And so we had to make a number of design choices that were going to center the use case or center the user, center Nuevas Voces, la comunidad de Olneyville here to do the best they can for their community. An example of this is EJ Screen. It's a beautiful aggregation from the EPA of all of these different layers that might have to do with environmental justice. It's a little overwhelming, it's a little sparse. What do you do with that information? They have this like points thing where they have schools, but the only thing that they have in that school's information is the address. It's just not relevant for the user. It's a great deep dive if you're ready to go there. It's got a lot of stuff, but for the average community member, how's that going to be useful? We also looked at this project out of Chicago, which was one of the reasons we were excited to be at IMSI, because they were trying to make this kind of information more easily accessible for advocacy use in Chicago. But Chicago has an amazing data center. Providence doesn't quite have that, so we had additional challenges. One of the things that we saw happening in the history of WRWC and collaborations, they would have interns come in from a local college, come in, build them a map. The map was in proprietary ArcGIS. Nobody could access the map. They didn't know where the database was of the origin. It was not designed to specifications that they needed. So now you're taking away control of their data and of their story, right? So providing the technological solution is not enough, right? You have to provide the agency. You have to really, they need to feel like they are the stewards of their own data, okay? So we had to really think about how is this going to be really accessible for them to maintain the data. Then we had to think about languages. We wanted Spanish to be first, and we wanted the information that mattered to them. They also pointed out that even though a significant number of immigrants are from Hispanic countries, it's not exclusively true, first, and second, just because they come from countries that were colonized first by Spanish, many of them still have as their first language indigenous languages. It's particularly true in Central America. And so they may speak Spanish, but they may not write or read Spanish very well. And some of them learn through that. Maria Jose, for example, interesting, she like speaks like 4 languages. She just was still working on her English, right? So here's what we came up with, vecina. Every good project needs a great acronym, and in Spanish, vecina means neighbor. Visualizing environmental and community information for neighborhood advocacy. And we started, eventually we would like to get into this broader sort of chives project that looked like Chicago did, but what we were doing is proof of concept. For each kind of information that they need, can we like give them some kind of resource map? And this is what it looks like. We helped them make a logo to express something about themselves. We named it, like how are we gonna talk about like community assets? Like what is the right word like in Spanish? And we ended up with fuertes, which means the strengths of the community, right? You can see there's an escucha button, which means that you can hear and listen to the description of the organization. The other thing was we started by thinking about a picture of the place that you were gonna see. And they were like, no, we need the picture of the people. We need the picture of the people, and that needs to be first. So I think these are things that we don't often think about in our design decisions, but when you have community partners that are running those design decisions, I think it really makes a huge impact. Here's another project that Victor did, working with this team. For clarification, we met and started this relationship with ISERM last summer, while we were at ISERM last summer. There's part of a semester program that we proposed at ISERM to bring a lot of researchers, faculty, graduate students, people in industry, whoever wanted to come and play. But due to various reasons, instead of running it in a semester, we were able to split it and run it across 2 summers. So we were there last summer and this summer. So we made first contact last summer, we hung out, we got to know your needs. And then I was also running a similar semester program, more like a month-long winter semester program at IMSI in Chicago. And so we were able to actually bring everyone from Rhode Island. IMSI paid, even for our community partners, which is a huge deal, paid for them to come to IMSI to spend time with us developing all of these tools to their specifications. And so our team had a few projects there. This is one of Victor's, because as they came over, again, we're like, starting to work on environmental information or something, and she's like, Jenny's like, man, I'm helping this immigrant family. They got to choose a middle school. I don't know what to tell them. Providence is sort of quasi-school choice. Like you're guaranteed something in a mile of your place, but you can choose anywhere in Providence. And it was due that middle school choice form was due right after. And the databases are not very helpful here. Like, what does it mean to you? None of them had a listing about exactly what English language services your child would get. Is this just going to be something like to check mark 504 and IEP, or is this going to be something that's like a dual language immersion school? And so Victor spent an extraordinary amount of time getting all that data and finding things like, okay, what kind of programs are available, and if they had very specific programs, like what kind of image logo can we give them, that little ES for Espanol, to indicate that those programs exist. And we got disaggregated data from English language learner outcomes on tests and language learner outcomes on tests. And I'm saying, which school would you choose? What do you see as the message here? The ELL is English language learners, and this meets or exceeds test proficiency. And you see that no school is doing justice for English language learning students. No school in all of Providence. It is so bad that the state took over all of the Providence schools a couple of years ago, just before the pandemic. But then we have newer information that shows that they've taken over Central Fall schools 20 years ago, and they're still not serving students even with state takeover. This is a huge, huge problem. And then what's happened is some charter schools have come up as a possible solution. That also, it's Victor's shaking his head. We just finished the analysis on this at ISERM. It's not good for charter schools either. This is a serious justice issue. The other thing we did while at ISERM this summer, so that's kind of the kind of where we were picking up from the time at IMSI, and then we came back to ISERM and continued to work with them. And we did a little bit of a healthcare flair to this same thing. And we focused on a few different things. We focused on data collection, trying to get information about Spanish-speaking doctors, simplifying and communicating health information, and again, resource maps and op-eds. A bunch of folks that are in this room are involved in various parts of that. But I'm very proud to say that I roped my 2 kids into it, and my daughter made those infographics, and so on Canva, because she's got a school account, she gets all of the clip art for free. And my son made the BuzzFeed quiz, which helps parents. Where should I go to take my child if they are sick? And goes through all of the questions. Do you have insurance? Do you not? What is your citizenship status? How much of an emergency is it, et cetera? And then it points you to the appropriate clinic or emergency room based on your needs. And that's already been shared in the community Facebook group, I've been told. So, and again, we did a resource map. For this, we started implementing code that would actually show 2 pictures, because we realized we needed them to be able to see which the entrance was, but we also wanted this infographic of what is available at that site. And then we have descriptions as well, and a summary of services, and so forth. So really, really exciting. We also did a series of op-eds associated with this work. Unfortunately, the Projo, the Providence Journal, did not want to use our op-ed. I don't know, it might be still in consideration, but whatever. but the Spanish-speaking newspapers were very excited about this. And so we have already sent it to 2 Spanish-speaking journals. That was primarily Omaira Ortega and Joe Hibden worked on that, and then also Jose Pabon and our community partners, Jenny and Maria Jose. There's also some others that are planned in the future. Chiara was working on, who's at Holy Cross, was working on an op-ed on the lack of health insurance coverage. I know Victor's like gotta tell this story about ELL outcomes. And then, you know, can we put it all together in a bigger set of stories and traditional publications? Okay. I kind of sped through that because I wanted to throw a few slides out from another project that I recently was working on with a few more individuals. You know, I kind of want to bring up the elephant in the room for a lot of folks. I think that this, you know, needs to be talked about, and I think we feel disempowered to not talk about it. What can we do? So the same way, you know, I was thinking about why Providence for me, that place-based, community-oriented perspective. I think we need to think about what communities, even here in this room, need our allyship, or in the state, or whatever. So I'm going to talk about a project that was looking at investigating we were the anti-trans legislation, but we were investigating some of these anti-trans legislation bills. For those who may have known Canon Ince, they had started a QR textbook, this was a chapter of that quantitative reasoning with our textbook that they had begun. And Bianca and they had collaborated to write a small grant together for the Rios Institute, which I direct, and had, you know, said we'd like to continue to work on it, but then Canon passed away. And Bianca was spending the summer with us at ICERM, and we felt like this was the place to help finish that work on that story, to contribute something so that Canon's memory would live on. I think that's just really important. I think, you know, from our community, extremely important to talk about. Canon also spent the winter at IMSI with us, not on the Nuevas Voces project, but working on a small town policing lab project. So there's some people here who are involved in this project. This was done as part of the education workshop that we ran at ICERM due to the semester program. And I'm not going to give you the whole thing, but I'll give you a little bit of the snippet that I worked on, which was what do the bills say? So we did some, there was some early analysis about how many bills, and 2023 is a terrible year already. I'll just put it that way. But there are groups that are keeping track of these, and then Mark worked to try to figure out the API to try to automate downloads of all of these bills. I did a lot of text cleaning to that automated pull, and then we just really sat around and kind of thought about what can we do, especially for the context of developing a QR chapter, what can we do that would have some impact? So we chose to look at word frequency. There is a larger possibility of a broader research project, and you can talk to one of us if you're interested in that. But this was just for the purposes of the QR book. And Victor, who's formerly a lawyer, helped us with understanding how to read these bills and clean them in ways that would work. One of the things we did is looked at the Given Name Act. So the reason why we looked at the Given Name Act is because the Heritage Foundation has a template for the Given Name Act language. And we looked at one of the states that had passed a Given Name Act, Arkansas. And we've got, interesting in the Heritage template, what I find is that there's a lot of public, state, education, employee, et cetera, there really isn't any big top 10, or actually I think this is top 20 word that says anything about names or pronouns or anything. Very interesting. You look at Arkansas, name is number 2. Birth, which is related to birth certificate, etc. We developed some initial hypotheses, and our initial hypotheses around this, or actually I should say, I think it was Mark's initial hypothesis was, this isn't about trans people. They're just a convenient excuse to test all of these things. What control do we have over education? It's a small enough marginalized population that this is the goal. But as it's been translated into different places of adaptation, it's become more about being anti-trans and talking more about names and talking more about birth certificates. It's not really actually, it's only a subset of the other plan. Then we looked at another one that was vetoed in Arizona. This one talked a lot about some of the same kinds of things, but pronouns shows up there as well, name, biological. They were starting to use the words biological sex. Fortunately, that was vetoed, but not great. But where's the hope? The hope, here's another bill, sort of called Given Name Act. It's actually called the Given Name Protection Act. And so this was passed in Illinois just in June 2023. And we see words, also, this one's very, very expansive. So this covers a lot more territory than some of these other smaller bills, but we start seeing things like services and care and family in ways that we don't see before. And I think that it's important to look at sort of the whole ecosystem. This is only computational text analysis is a lot more involved in not just word frequency or word clouds or something like that, but I think this is a very tractable thing that any QR student could do and already tells you a little bit of that story. And so I think it's really interesting, and I wanted to share that. There are definitely next steps. We'll continue our work with WRWC and this chapter, which is a lot of the analysis is done, but still has much writing. I'm teaching a PIC math course in the fall, and actually I'm going to have student groups working on both of these projects as part of the PIC math, because I have community partners with WRWC, I have community partners with Rios Institute and their sponsorship of the OER textbook, and with now with Math for the People and other folks. So I think there's lots of room for continued work. I'll also point out, for those who are looking at where is the opportunity to read some more, we just had a special issue of the Journal of Humanistic Mathematics published this week. And so if you want to look at that QR code, it should bring you directly to that special issue. So thanks.
All right, thank you. I'm glad I made it. The backstory is I landed at Tampa Airport at 9:40. Okay, so usually you would start a talk with a land acknowledgement. I want to start with what I'm calling a Florida acknowledgement. So I'd like to acknowledge that Florida lawmakers have enacted legislation that targets, terrorizes, and torments members of the LGBT community. Florida lawmakers have explicitly diluted the voting power of Black and Latino communities. Oh, that's hard to read, but Florida lawmakers have explicitly endorsed educational practices and curricula that bolster white supremacy and promote compulsory heterosexuality. Florida lawmakers have endangered lives by enacting nonsensical gun laws and anti-scientific COVID-related policies. Florida lawmakers have enacted legislation that diminishes women's personhood, bodily autonomy, and constitutional rights. And Florida lawmakers have declared their opposition to equity, diversity, inclusion, and social justice in academia and other settings. If you want to see them, see it that way. Okay. See what I did there, right? Okay, just checking. All right, so here's the outline of my talk. I'll sort of give a shout out to the MetaMath crew, give some definitions of what is this MetaMath thing anyway. I'll give some definitions of quantitative justice, which you might have already seen earlier in this session. I'll talk about the goals, challenges, and opportunities of the MetaMath project. And so the bulk of the talk will be describing 6 MetaMath examples. And then we'll conclude with an invitation for you to get involved And of course, there are obligatory memes. All right, so here's the MetaMath team. This is an incomplete listing. I'm just pointing out that sort of it's a diverse group in seniority, from people who have not received their PhD yet, from people who have received their PhD decades ago. And yeah, and so some of those people are in this audience. What? Is there a thing? It's really hard. Oh yeah, really, oops. Really, Carrie Diaz-Eaton, who else is there? Oh, Giacchini, and others. And this is a lot of other people are working on MetaMath that are not sort of listed here as well. Okay, so here's some definitions. As Carrie mentioned, there was a data science and social justice program at ICERM last summer, and hashtag MetaMath started as a Slack channel to organize ourselves, the sort of rotating group of people that were interested in working on this project. And what does MetaMath mean? We think of it as sort of using math, lowercase, sort of quantitative tools, topics, and techniques to analyze math, capital M, which is the math community. And so formally, we call that the mathematics of mathematics, which is a sort of a play on, is informed by something called the science of science, which is known as sci-sci, and it's a sort of a burgeoning interdisciplinary movement which thinks of the process of developing science, analyzing that scientifically as well. So we're using mathematics to analyze math, they were using science to analyze the process of creating science. And so that's really where MetaMath came from. Math didn't make any sense, so we went with MetaMath. Okay, some more definitions. MetaMath is not metamathematics. That is a branch of logic. I think of MetaMath as an organizing space for people, research, and energy to make mathematical sciences community more equitable, diverse, accessible, inclusive, and just. And the key idea about MetaMath is that it's a quantitative justice project that uses analytic tools from math, data science, and the social sciences, and then applies them to the mathematics sciences community itself with an explicit goal to promote social justice. And so what is quantitative justice? Here's two definitions of it. This is my definition. The application of techniques, tools, and topics, yes, I like alliteration, from the quantitative sciences in subject domains that are derived from or typically associated with the social sciences, again, with the explicit goal of promoting social justice. So MetaMath is a quantitative justice project. And if you like pictures better, then think of, you have sort of, oops. Okay, I can't see my pointer. At the top, quantitative methods and techniques from STEM and social justice and the desire to do good in the world, and context associated with social justices. QJ, quantitative justice, is that sweet spot right in the middle. And then mathematics would be sort of in that QJ as well. Sorry, MetaMath would be there. Okay, what are the goals of the MetaMath project? To promote, I'll just call it JADE, in mathematics by uncovering, documenting, and highlighting the existing inequities in the mathematics community. And there's a reason why we're doing that. We want to quantify and evaluate where we are now, the status quo, in order to be able to establish benchmarks so that we can know sort of basically how bleeped up stuff is and when change occurs, that we can sort of document our progress. And maybe by depicting how bleeped stuff is, it'll catalyze people to want to change the math community as well. And there's a really interesting third goal, which is that by demonstrating that you can use math to promote social justice, we believe that will sort of be more attractive to students who are always asking, what can I do, what is math being used for anyway? And so we're showing that math can be used to promote social justice about issues that people might be personally invested in and interested in. Okay, challenges and opportunities. Oh yeah, I'm ahead of time. Okay, challenges, data. Data is actually a challenge and an opportunity because there's always, you always want more data. There's a lot of data out there, but there's the lack of appropriate, accessible data about the mathematical sciences community itself. I mean, there are sort of the usual suspects, I guess. The most sort of largest sort of data source is the quinquennial, every 5-year survey by the Conference Board of the Mathematical Sciences. The 2020 version is not out yet. It's supposed to be out any second now. So you usually have to look at the 2015 version. And there are sort of larger government entities generally that collect data about STEM entities, and they often have data about math as well. That's NCSES at NSF and SES at Education Department. But one of the other key challenges of doing metamath, using math to analyze the math community, is trying to convince existing gatekeepers that doing this work is actually valuable and an aspect of mathematical research in of itself. And this is sort of, we've recently been having encounters with some of these gatekeepers as metamath people have tried to submit papers to journals, and journals are rejecting them, saying, this isn't math. So it's the whole thing. As I said, stuff is sort of bleeped up. There has been increasing attention and commitment to JADE in mathematics, and this sort of provides a little window opportunity, perhaps, for something like MetaMath to analyze data, and to analyze the mathematics community sort of to promote social justice. The fact that people are actually thinking about these issues sort of makes a space for MetaMath to do its thing. And as I said, data is sort of a challenge and an opportunity. We are still awash with data. And so there's also data about the mathematics community, but often it would only include maybe demographic data in one characteristic. It won't include all the other characteristics that we might like. For example, you're going to see later, we have data about gender in mathematics. We don't have that much data about sexual orientation in the mathematics community, and race, ethnicity stuff can be complicated and problematic. Even the gender stuff is problematic. I'll tell you in a second. So that's the end of the sort of intro, sort of what MetaMath is, what we're trying to do, the goals, challenges, and opportunities. And now I'm going to spend roughly 10 minutes going through some examples. So this first example is hot off the press. As Carrie mentioned, Journal of Humanistic Maths published this article called On Definitions of Mathematician. And so as we thought about MetaMath, as we began our work, we thought, well, what is the mathematics community? And the people involved at the time had all sorts of experience with, some of the members of the group did not view themselves as mathematicians, right? Because data science can be people from all sorts of disciplinary homes. And we had experience with people thinking about, oh, mathematician is this, or mathematician is that, or you're not a mathematician, or you don't look like a mathematician. What does a mathematician look like? Okay, so we used a framework that was based around 3 kinds of definitions: a function-based definition, a qualifications-based definition, an identity-based definition. So a qualifications-based definition would be a mathematician is someone who has ever taken an algebra class. Right? Or a mathematician is someone who has a PhD in math. Some other entity has said you are qualified because you have this little piece of paper on it. And then we sort of described different kinds of whether definitions could be expansive or exclusive, narrow or broad. That's where we started. So that's one example of MetaMath. I'll go through the others faster. This also is from JHM, just came out. This was an analysis of the hashtag #DisruptJMM tweets. And I showed this because it's this lovely picture, oh, there's my thing, showing sort of the interactions between people who had retweeted or quote tweeted various tweets with the hashtag #DisruptJMM. And you can sort of see over time, sort of as JMM approaches in January, the number of uses of the hashtag #DisruptJMM tweet increases. Okay, the next 2 examples use a pretty sort of unique data source the mathematics community called the MGP, or the Mathematics Genealogy Project. Easy for me to say. And so this is a database which, it goes back hundreds of years, and if someone has a PhD and they have an advisee who then gets a PhD, it sort of you form a tree structure. So, for example, I got my PhD under Professor Julian Cole and Professor Don Schwendeman at RPI, and then they got Julian Cole got his PhD under Herb Keller, and so you'd see this tree of sort of people who got their PhD and who they got their PhD from, and people can sort of trace their lineage, their mathematical lineage, back to people like Gauss. And so this is a mathematical model of trying to see if using this tree structure over here, again, it's disappearing. I can't, oh, there it is. The yellow are women, and the blue are male, and they're trying to see if they do this model, can they sort of regenerate the actual data of the percentage of women over time in the MGP. Okay, speeding up. Yeah, doing okay. This is another analysis using the MGP, but this is, right, as I said, I'm in the MGP, but sadly I will have no children because I'm at a liberal arts college. So by analyzing a subset of people in the MGP who they have a parent, so they have an advisor who they got their PhD from, and those faculty then had their own advisees as well. If you restrict yourself to that set of people, basically doctoral granting faculty is what the description is trying to say. If you analyze the entire network and use network analyses, you can come up with what's called centrality analysis, which gives you a prestige ranking. So the more PhDs that your people at your department produce, the higher your prestige ranking will be. And then this graph, I'm going to try it. Yeah, there it is. It sort of says it, right? The green solid curve sort of tells you the number of math PhDs that have been awarded over time, and then the blue is the number of PhDs that those people produce over time. And the reason why there's this sharp decrease over here, because the recent graduates would not have had enough time for their sort of children to also have produced PhDs. But they have some really interesting analysis in this paper, which, for example, surprisingly shows that departments that you would have thought had more prestige over time has varied. For example, Yale was considered one of the top PhD programs, but over time it actually has been decreasing. And Carnegie Mellon had sort of the greatest increase over time in sort of prestige ranking. And it's sort of, so what's interesting here is where you can sort of quantify the sort of the unquantifiable nature of sort of prestige and elitism in the mathematics community. Still trying to go faster. Okay, the last two are from a paper we just worked on at ISERM in 2023, which is still under reviews, called Quantifying Inequity and Documenting Elitism in the Mathematics Community. And as I mentioned, right, we have good data on mathematics faculty. So this, I presume, famous paper now by Watman, et cetera, in Nature last year, looked at a very large data set, 300,000 faculty over 10 years, 2011 to 2020. And they have so every academic discipline that generates PhDs in the United States. And we looked at it and sort of excerpted the mathematical sciences disciplines. So that ended up being about 10,000 faculty. And if you look at the data, the clear thing you should see is that the red, green, and orange lines are much lower than the blue line. The blue line is the percentage of women in all academic disciplines that are women. And as you can see, we have sort of mathematics, operations research, and statistics, and mathematics 16.8% on average over the period from 2011 to 2020 were women in departments that grant mathematics PhDs. Okay, so I think that's problematic. I hope you do too. Here's another example of documenting elitism. So when we looked at that percentage of women in PhD granting departments data and compared it to average annual funding by the National Science Foundation called the Division of Mathematical Sciences. And we looked at the different departments. And so what's here is that it's a little complicated. So there's a larger data set of 200 and something PhD granting departments in the United States, but only 161 of them have a prestige ranking that Whatman, et cetera, had produced. Using that prestige ranking, we took the top 25%, turned them into blue dots, and then we graphed all of their sort of average DMS funding over the decade. And what do you see? What do you wonder? Do you notice that there's a lot of orange down here? So that's the bottom 75%. But as the percentage of women goes up, hey, there's no blue dots over here. And you might notice that there's none of these that get more than an average of $2 million in DMS funding over that period of time. And so this sort of we would argue that this demonstrates sort of the existence of an elite in mathematics. One of our projects in MetaMath is saying that the math community should sort of reconsider and re-envision what elitism means. And for us, we think that departments that do a better job, that are more diverse, that have more women in them, we should think of those as elite departments. Those are the people that are providing opportunity for as many people as possible. Okay, and that's the last of my examples. But I want to end with an invitation. You can join us. And these things are online, they're ongoing. QSide is the quantitative study for inclusion, diversity, and equity. It's a great project. They've been doing quantitative justice stuff since they've been founded, I think, which was 2019. That's the Data for Justice Accelerator Program, and we're all about the Slack. And so you can join us, go there and sort of get an invite. There's some QJ stuff happening at MSRI, actually in a couple weeks. It's starting, it's a semester-long program in algorithms, fairness, and equity, and hopefully more information coming soon. The second Math and Racial Justice workshop will happen in summer 2024, also at MSRI, SL Math, and since I'm the organizer, or one of the organizers, there's definitely gonna be some MetaMath there. And here's the references for the 6 projects that I talked about. And of course, obligatory means. So I'll just let you read these yourself. So thank you to the organizers of this session, y'all, and my co-authors and members of the damn crew. It's my slides there.
Thank you, everyone. These speakers, do we have any questions?
Don't be shy. All right.
I have a strong question. You're pulling a lot of information from sort of publicly available spaces. So was there some sort of like scraping tutorial, or like, I guess I'm curious, like how you went about just grabbing it and then sort of I guess, okay, let's see. Was it sort of there was someone who kind of helped collect that data, get it to like a certain point, and then the team started to interact with it, or was part of the work learning how to do this?
Right. So the question is basically how do you do this? So there's data available, and so were the people involved like, I don't know how to do this, but it's a member of a team. And so yes, a lot of this data is publicly available. Like for example, the NSF funding data. And I believe the person who scraped that data was Drew Lewis. And so he got the data for us, and then Rachel produced the beautiful graphs. And so it's a team effort, but in almost any data science project, as people probably know, 90% of the work is in the obtaining and cleaning of the data. There's some, at one of the workshops that we had during the program, someone was saying like 90% was getting the data, and then like 9% was maybe programming, and then analysis is this little 1%, because that's how much sort of effort it takes to do this stuff. And yeah, that's where, when I talked about data, the fact that there is some public data available, but it's in this particular forms. And for example, even this huge Whatman data set that we have, which I forgot to mention, the gender of the people there was imputed by name. There are algorithms that have been trained on very large data sets, so if a person is this name, then like mine, Ron, there's some percentage that person's going to be male, but maybe not. And what do you do with someone whose name is Sunrise or Snowburst? And so we only include in the data set the fraction of people whose imputation of gender that we knew was up to about 85%. So there's a significant portion of the data is not included as well. So there's always these things you have to do to the data to make it usable before you start your analysis. Thank you for the question. In the back, BK.
I'm curious about your publication strategy, both overcoming the resistance to publishing some of this and getting it in front of the right readers.
Did everyone hear the question? The question is about the publication strategy and thinking about sort of where to publish in order for the people who are interested in seeing the work, will they be going to those fora? Honestly, we haven't been thinking about that as much. We've just been trying to get it out there. We do think that JHM was a good place to start because presumably people who tend to go to JHM would be interested in sort of thinking about the implications of the intersections, I would say, of mathematics and social justice, data science and social justice. But for example, when we did get rejected from a journal that will remain nameless, we were invited to repurpose that paper and to make it more mathy, and that's sort of what we did. And we think that's fine. I thought that was fine to do in order to, because we really do want all kinds of audiences to see that this is mathematical work and it should be considered valuable. And there is a lot of math and computation that happens in it. And so yes, so I do think we are trying to put the work out in as many fora as possible that it can get as wide a view as possible, within reason. Yeah, thank you for the question. And any more? Yes?
I have a few questions about the conference, math and racial justice.
Uh-huh.
So first, where is it? Second, I'm a statistician, not just mathematician, so would that be relevant? And next, I'm a disability includer researcher. Is that, because I think identity is not isolated, so that's the title is racial justice, so I was wondering.
Okay, so the question is about the mathematical justice workshop. So the first mathematical justice workshop was all online and hosted by MSRI, SL Math. I don't remember now. Summer 21, I believe, and that's available at the msri.org or slmath.org website. The video presentations are there. We've put in a grant proposal to fund the 2024 and 2027 mathematical justice workshops. I think we still haven't heard back on whether it's going to happen, but we are going to sort of work as if it is going to happen. So yeah, so the plan is that it will be in person during the summer at MSRI, which is in Berkeley. And It is explicitly about math and racial justice, and I believe I can speak for the co-organizers that we do take an intersectional lens. So even though the focus is racial justice, and we haven't decided what, actually I think we did say, we made some suggestions of what the themes would be, but those are open to change as we schedule. The themes before were things like health disparities, were things like fair allocation representation, math education. That was in the first one. So we were still trying to decide, are we going to repeat those or just go in completely new directions for, like we could talk about, gender and racial justice or other identity characteristics of racial justice, or, what is race? Yeah, so stay tuned for more information as it comes, okay? Any more? Another one. Okay, last one, I think.
So a kind of naive question, but you talked about the difficulty of finding the basic data on the mathematical community climate. Just in your personal opinion, do you feel like, I tend to think of professional organizations at first, and two, is some data is really insufficient. Is there any momentum towards improving this?
A really good question. One of the hats I wear is Vice President for Equity, Diversity, and Inclusion at Society for Industrial and Applied Math. And as in that capacity, I have been pleading with my counterparts at other math organizations, say, hey, let's get together. Let's talk. Let's form something to try and sort of think about this issue, sort of math community wide. And sadly, I've been making efforts, and it's slow going. It is true that one would think that the math associations would be the sort of first place to think about collecting data about the mathematics community. But every institution, every math institution sort of has their own members, and those are the people that they're collecting data about. For example, the CBMS and the annual survey, so AMS does that sort of on behalf of the community and makes it available. But generally, each of the communities, each of the institutions, each of the organizations has their own membership list, and they don't want to share that with people. Yeah, that's not, I wouldn't call that publicly available data. One of the things as sort of part of the MetaMath project is advocating for increased data collection and data access by the math community. And that's sort of a policy component that is sort of nascent in my mind. But for example, as part of the On Definition of a Mathematician project, our next step is to do a survey and really think, and to ask people, when you hear mathematician, what do you mean? What kind of definition works for you? Is it function-based? Is it identity-based, et cetera? And sort of to really sort of generate our own data, because the data isn't really available about how people think about this. But yeah, so I think I don't want to keep you all from lunch or whatever.
Fantastic.
Thanks.